Hey guys, welcome to another one of these videos in preparation for your exam. In this video I'm going to be doing the 2010 Mechanics and Materials exam, question 1. The question looks like this, which you should have access to. Am I getting it in the screen? Yeah. Okay, so first thing I guess is this is a bit of a weird situation, and you should try and understand why it looks the way it does. So the first thing, of course, is there's a horizontal beam here with the load. Okay, so this is the only load, and it's a distributed load, obviously. And there's two columns, if you like, holding up that beam that has a distributed load. In between there is a rigid beam. If you read the question carefully, there's a rigid beam, which means it can't buckle. And then there's these two guy wires. Now why are they there? Well, I could go into a more detailed explanation, but basically they're going to stop B and E from moving horizontally. Okay? The purpose of this rigid beam and these wires is to stop the beam moving, to stop points B and E moving horizontally, in effect constraining these columns in the center. Okay, so the first thing is you've got to understand that diagram. If you don't understand why these wires or this beam is here, then it's not going to make a lot of sense. It's going to be very hard. Okay, so now that you know that, let's get to work. So question A, and I'll assume you've got this with you so you don't need the question there on the screen. Part A asks you to determine the compression load on the vertical columns A, C and D, F. Okay, so what is the load on this system? Well, we have that horizontal beam at the top, and it has this distributed load, which is, call it Q. Okay, the distributed load Q, which has units of newtons per meter, of course. Okay, which means there's a net load downwards of Q times the length, L, which in the question it says the length of that beam is L. And that is supported on either end by those two columns, AC and DF. So that means there's two reactions or loads in AC and DF. So this is the reaction which is also the load in AC, and this is the reaction which is also the load in DF. Now, this is a symmetrical problem. Shouldn't be too tricky, just from simple equilibrium. You can clearly see, I hope, that both of those loads are going to be half of the total distributed load. So the load in both of the vertical columns is QL on 2. That is, the load in these columns is QL on 2. Okay, so that's part A done. B says, prove that the distributed load to buckle AC and DF, I'm going to need this here now. Prove that the distributed load to buckle AC and DF is this equation. Okay, that looks a lot like a buckling load equation, so in fact that is what we're going to need. So perhaps we should start with that. Critical load for buckling as we found out, and I expect you to remember, is the critical load PCR in the column is equal to n squared pi squared on L squared times EI. Now in our case, the load is not, well, we know what it is. It's this, so we just substitute that in there, and we'll get our critical buckling load in terms of Q, because that's the only applied load into this system. I think we'll leave that there. Okay, so if the load in the column is Q, the critical load is QCR, it's got to be equal to the right hand side of that equation. And we just rearrange that quite simply, and that should give you this equation, which is the answer. Okay, so it's an easy one. As long as you remember this equation, which I asked you to, you can do this question fairly easily. Okay, so, and as I said in the previous video, or I've said before, I tend to write questions where 80% of it is fairly easy and 20% is more difficult. Okay. So the difficult part is not always at the end of the question. In fact, in this case, the difficult part is coming up right now in part C. So part C says, determine the maximum stress in the horizontal beam. As soon as you hear the word, or read the words maximum stress in a horizontal beam, you think flexure. So max stress in horizontal beam means flexure. So read flexure. By flexure we mean sigma max is equal to the maximum bending moment that we can find in that beam times the maximum distance to the neutral axis, C, divided by I. Okay, so this is what the question is asking you to find, and that is the first difficult part of that question, I suppose. You have to be able to interpret it that way. Then it says, it doesn't finish there. It says the maximum stress in the horizontal beam, what does it say? Just before the columns AC and DF buckle. So just before the load, let's say, when the load is this value. Okay. The beam is rectangular, and it gives you the cross section in the question, 40 millimeters by 20 millimeters, height times depth. So the cross section looks like this. And that's going to be our C value, so the depth is 20, the height is 40 millimeters, making C, this value here, it's the first thing you should be able to write down. C is just going to be equal to 20 millimeters. Okay, so we know C. I believe, is given in the question. All the beams are the same, it says in the question, and I is equal to 2.4 by 10 to the minus 8, I think, meters to the 4th. Okay, that's given in the question. So all that remains is to figure out this M max. And remember, this is all in the horizontal beam, and the only thing that matters about the columns is they're about to buckle. So this is the load. So then the problem becomes how to find M max. Okay, we're asking for the bending moment inside a beam, so we do a free body diagram. We take a cut. We have, let's say, we'll do it here. Take a cut of this beam, it has a distributed load Q. Okay, we're just going to take a little cut, so this is a length X. Okay, there's a reaction here, so you could treat it just as a simply supported beam with a reaction QL2. We've taken a cut, so there's a shear force inside this beam, V. In this is my definition of positive bending moment that way, positive shear force downwards, and this is a load Q, and that has a net force downwards of Qx, which acts at a distance x on 2 from this location, from the edge of the beam. Okay, the equilibrium tells us you should be able to see V is equal to the difference between QL2 and QX. So it's QX minus, sorry, QL2 minus QX. And the sum of the moments gives you M is equal to, if we take the moments about this point, M is equal to Q times x on 2, which is in the opposite direction, so Q times x on 2, Qx times x on 2, rather. And then this is in the opposite direction, so that's plus Qx L on 2. Okay, so if you work out where the maximum is going to be, so the maximum bending moment, if you think about it for a bit, the maximum bending moment, of course, in a symmetrical beam is going to be at the center of the beam. That's where the bending moment is the maximum. In a symmetric loaded beam, I should say. So the maximum is going to be at x equals L on 2. So substitute x equals L on 2 in there, and you should find the answer is QL squared on 8. Okay, and that's equal to the maximum bending moment. Okay, so you can shove that in to the maximum stress, and you get QL squared on 8, sorry, times C, which was 0.02, divided by I, 2.4 by 10 to the minus 8. Okay, we know L is 4 meters, and we know Q is QCR, so we end up with L being 4 meters, so 16 on 8 is 2 times 0.02 divided by 2.4 by 10 to the minus 8 times QCR. Okay, we need to work out what QCR is for this case. If you remember from before, the answer to the previous question was QCR is this value. Now this has got an N in it, right, which is the buckling mode. We just need to make a note here that this question, recall that this question has this strange guy wires and rigid beam, which I said was stopping B and E from moving, which means this is a column that is supported in the center, which means it's going to buckle if it buckles like this. And that, you should all be realizing, is mode 2 buckling. Okay. So we can actually calculate the critical load, QR, because we know N, we know all these other properties. So if you do that, you have QCR is equal to, what was N? N is 2, so it's N squared, it's 8 pi squared E I on L cubed. And if you stick in all the numbers, I won't write them in here, so waste your time. you get 5921.8. Probably don't need the 0.8 newtons per meter. Okay. And then if you substitute that into, I'll write it down again, into our sigma max equation, what do we have? Sigma max is equal to 0.04 and 2.4 by 10 to the minus 8 times that, and you get quite a large number. (9.87 gigapascals). Okay, quite a big number. Alright, but that's the answer. Okay, part D. Part D asks, if the yield stress was 200 megapascals, which one would happen first? Would this cause buckling? Would the horizontal beam yield because the maximum stress is past the yield stress? Well, obviously it will yield first. You only need sigma max to be greater than sigma y, which is 200 megapascals, to yield first. Okay, so once this sigma max gets past 200 megapascals, it's yielded. But in order to buckle, you need a sigma max of 9.8 gigapascals. So clearly it yields first. Okay, the last part of the question, part E, says if you remove these guy wires, if you remove these and this beam, right, so these are all gone, what that basically means is B and E are free to move now. Now if this is all perfectly symmetrical system, it won't topple over. So if the load gets high enough, theoretically AC and DF can buckle, however unlikely that is. But the point is now, if B and E can move independently, then you can get buckling like this, which is n equals 1. Okay, so that changes the problem, because now your QCR for n equals 1 is less. So now it's just, instead of 8, it's 2 pi squared EI on L cubed. And you can shove that into your equation and you'll find, well, we can calculate that, it's much smaller. Okay, so you can shove that into the sigma max and you'll find that that's equal to 2.47 gigapascals. So the answer is nothing changes in terms of your answer to C and D. It will still definitely yield before buckling. Or, sorry, the answer to D doesn't change. There is no change. Still yields first. Okay, and that's question 1 of the exam in 2010.